Good afternoon. So, I will tell you a little bit about what we do, and we work primarily in the area of algorithms, and in particular we work on what are called approximation algorithms. Before I get to this, let me first tell you a little bit about what algorithms are, what efficient algorithms are, so that we can build the context for approximation algorithms. So, algorithms is a recipe, is a way of specifying the steps needed to solve a problem, right. You could suppose you wanted to, given a set of numbers, you wanted to put them in increasing order, right. So, what would be the way you would do this, right. So, if you list out these steps, that is what an algorithm would be. And computers are used for solving many different kinds of problems, right. So, whether these are problems involving sorting numbers, searching in a database, or more complex problems, let us say multiplying two matrices, or we will see examples of even more hard problems that computers are used day in and day out to solve. And so, for each of these problems you need to design algorithms. You can design many different kinds of algorithms for a problem, but you would want an algorithm which is efficient. Okay. So, what do I mean by an efficient algorithm? So, you would want your algorithm to run in a small amount of time, right. Why? Because these problems that you are solving usually are very, very large, right. If you are doing some weather modeling, you are typically working with matrices which are millions of entries, millions or billions of entries, and then even if you would have to do something which is like a simple matrix inversion, you need to have an efficient algorithm to be able to do that. So, efficient here means that you want your algorithm to run very quickly. Okay. So, we are in the business of designing efficient algorithms, that is what we do. For some problems, we can design efficient algorithms, right. You all use your navigation, right. So, if you want to go from a place A to a place B, you would use, let us say, Google Maps. You would specify this is where you are starting, you would specify this is where you want to be, and then Google Maps or whatever navigation software you are using will compute the shortest route to go from A to B, right. This is a problem which is efficiently solvable, right, for which we can design fast algorithms for solving these problems, even if the map on which you were working was humongous. Even then you would be able to do that. Okay. So, so problems of this kind, so problems for which efficient algorithms exist. So, computer scientists call such problems as belonging to a class P, P standing here for polynomial time. So, I will not get into what polynomial time means, but what you need to understand is that if you can solve the problem efficiently in a small amount of time, then these are nice problems. We will call them that these are in the class P. Okay, what are other examples? So this problem that I just told you, find the shortest path from A to B, right. This is a problem in the class P. Or if I were to say, sort a set of numbers. Let us say I give you 1 billion numbers and I say put them in increasing order. Again, you can come up with a very, very efficient algorithm for solving this. So, lots of problems that you come across, let us say multiplying two matrices, computing the GCD of two numbers, for all of these there are efficient algorithms possible, right. So, that is very nice. But then there are millions of problems which are very important for us to solve and for which we do not know any efficient algorithm. So, what do I mean we do not know any efficient algorithm? So, okay, let us take an example to begin with, right. So, I just said if you want to go from A to B, you can find the shortest path, right, and there is a fast algorithm to do that. Suppose instead you one Sunday morning your mother said, okay, you know, these are a bunch of errands you have to run. You have to go to the bakery to pick up something, then you have to go to the laundry, you have to go to somewhere else, and so on and on, right. So, you have to go to a set of points, and there is no particular order in which you have to visit these. You could visit them in any order that you wanted. Okay? But now what you want to do is you want to find the shortest way of visiting all of these points. You understand the difference between from the earlier problem? Like earlier, I just gave you some 2 points and I said find the shortest path between them. Now, I am saying you need to visit all of these points. Whichever order you want, fine, no worries. But the path that you take should be the shortest possible. Now, if you were to solve this problem, the big question or the first question that we will have to figure out is what order should I do these tasks in? What order should I visit these points? Okay? So, suppose these were 20 points, right? Your mother had a lot of work for you, so you have to do 20 different tasks that morning. Now, how many different orderings are possible for these 20 points? Right? So, if you think about it, it's about 20 factorial, right? And 20 factorial is a huge number, right? Given an ordering, suppose I said first you need to come here, then you need to come here, then you need to come here. Suppose I gave you an ordering, then it is easy to compute what the best route is. Why? Because then you will take the shortest path from here to here, right, which your navigation can give you. Then you will take the shortest path from here to here and to here. Let us say this was the 5th, the 6th, the 7th. So, you will, and then let us say 1 was your home, you would go back in that way. So, if I gave you the ordering, then you can figure out what the best solution is. But how many different orderings are possible? 20 factorial, and 20 factorial is a huge number. If I were to look at each one of these orderings and compute the solution, that is going to take a huge amount of time. 20 factorial is still not such a large number maybe, but you know 20 is a very small instance what we would call for this problem, right. Typically for these problems, and this is a class of, this is a problem is called, it's a very well known problem called the traveling salesman problem. In the applications where these problem arises, it's common to have, you know, let's say 1,000 points. Okay? And then you have to figure out what is the best way of visiting all of these points. And if you were to do 1,000 factorial, well, 1,000 factorial is beyond the capability of, you know, all the computers put together, right? That's just too large, right? 1,000 factorial would be something like 1,000 to 1,000, and you know, already 2 to the 40 is more than the number of particles in the universe, right? So 1,000 to the 1,000 is a huge, huge, huge number. So these problems, and this is not just one, there are hundreds and thousands of such problems which appear a lot in daily life, right? You might think of this as a contrived problem, but you know, I could give you many more examples which are very natural problems. Let's say you wanted to schedule the exams at IIT Delhi, right? This is called the timetable scheduling problem, right? So what is that? For every exam, you need a room for that exam, and there are a set of students who have to take the exam, and you have to figure out a time slot for that exam, and you have to make sure that a student who is writing 2 exams, you know, those 2 exams are not happening at the same time, or maybe one after the other, immediately after the other. So you have to give a sufficient gap between those exams, right? So if you bring in these constraints, again this becomes a very, very hard problem. And so these, okay, so there is again a class, these are a class of problems called NP, right? I will not even tell you what NP means, but just, you know, just take my, you know, just think of it as a set of problems for which we do not know any efficient algorithms, right? We actually, so that's one of the big questions in computer science, whether there can ever be an efficient algorithm for these problems. We don't even know the answer to that. We have not proved that there can be no efficient algorithms for these problems. By efficient, I mean that runs in a small amount of time. The best algorithm that we know for these problems take a huge amount of time. Okay? And so these are important enough that they come, that researchers have been over the last 40, 50 years that these classes have been defined, been working very hard to try and solve these problems. Okay. What do we do? Now let me come to approximation algorithms. So we know that solving this problem, finding the best route here, visiting these 20 points is hard, right? It will take a huge amount of time if I have to solve it exactly. So then we lower our sights a bit. We say, suppose we do not want the best route. Suppose we want a route which is close to the best, close to the optimum. Can we do better? Can we then get an efficient algorithm for it? Can we then get an algorithm which will run in a small amount of time? And the answer is yes, right? And that's the area of approximation algorithms. So what are we approximating? We are approximating the solution, the quality of the solution. We are saying we don't necessarily want the best solution, but give me a solution which is close to the best. Okay? And so we are interested in finding solutions which are still very good, but can be computed very quickly, right, in a small amount of time. So that's the area of approximation algorithms. To give you an example of approximation algorithms, so we could even, for instance, take this traveling salesman problem, right? And what is known about this problem is that there is, so this was, so I can now write the statement, the approximation algorithm. So you can get an efficient algorithm. So there exists an efficient algorithm for the traveling salesman problem that computes a solution within 1.5 times the optimum. Okay? So what does this statement mean? This means that we can come up with an algorithm which will not take too much time. So it will not take time like 1000 factorial if there were 1000 cities. It will take time only like 1000 squared, which is not too much, right? It's 1 million units of computation which can be done in a fraction of a second. So it will take time like 1000 squared. It will not give you the exact solution because that we believe is very hard to obtain using an efficient algorithm. So, but it will give me a solution which is within 1.5 times the optimum. So if the best way of visiting these 20 points required me to travel a distance of, let's say, 25 kilometers, then the solution that I get using this would never be more than 1.5 times 25, okay, provably, right. So this is a mathematical statement, this is a theorem, right, which means that for any set of points and distances between them that you give me, it will always find a solution which is no worse than, right. It doesn't say exactly 1.5, it says within, which means it is no worse than 50% more than the optimum. Okay? So that's the kind of a statement. So this would be an approximation algorithm for this traveling salesman problem, and we try to design approximation algorithms for a wide variety of problems. Traveling salesman is one problem that I'm very interested in, but have not been able to work on it yet. There's a question, so you can take that.
Sir, but then do we know the optimum? So as you stated that the solution lies within 1.5 times the optimum, but then we don't even know what the optimum is.
Yeah, this is a good point. So we do not know what the optimum value is. How can we say that our solution is within 1.5 times the optimum? Yeah, so we can compute some bound on the optimum. So given any instance, we call this an instance. By an instance, I mean, a set of points that your mother says you have to visit. right? Given any instance, I do not know what the optimum value is, and figuring out what the optimum value is actually very challenging, is very hard. But I can usually say, oh, the optimum is going to be greater than 20. Looking at the instance, I can figure out, again this will be a mathematical statement, I am not just playing by a hunch. The optimum is going to be greater than 20. Here is a solution which is within 30, and so this solution is within 1.5 times the optimum, right. So, we will provide some kind of a lower bound on the optimum value and give a solution which is within 1.5 times that lower bound, right. So, this is how all of this works. Okay. So, there are lots of very interesting questions here, and let me tell you what one question that that I find very exciting, that I like working on, related to the traveling salesman problem. And this is more graph theoretic for those of you who are familiar with graphs. Suppose I give you a graph. Okay, let me draw what's known as the Peterson's graph. Okay, here is a graph, 10 vertices and 15 edges. So, similar to the traveling salesman problem, right. Now, suppose I tell you, I promise that there is a Hamiltonian cycle in the graph. Okay, what is a Hamiltonian cycle? A Hamiltonian cycle is a cycle that visits all the vertices. Okay. In this graph actually there is no Hamiltonian cycle, but suppose I had given you a graph which is slightly different. Is there a cycle here that visits all the vertices? Yes, very simple. Yeah. So, if you went like that, so think of it as roads. Can you go from one point and visit all the points and come back to the starting point without repeating anything, right? So, that is what a Hamiltonian cycle is, right. Suppose I had something like that. Do you think there is a Hamiltonian cycle in this graph?
Yes.
Yes. What do you think would be the Hamiltonian cycle? Suppose I number these vertices 1, 2, 3, 4, 5, 6. Can someone tell me, whoever said yes, what the Hamiltonian cycle is?
164325.
164325. But you also have to get to the starting point. It's not a cycle till you come back to the starting point.
Can we touch the point twice?
No. So, in a Hamiltonian cycle, you have to visit every point exactly once, and you have to, it's a cycle. So, cycle means you come back to the starting point. Okay. So, not possible actually, there is no Hamiltonian cycle in this graph. So, okay, I give you this graph, huge graph, right, so that you cannot even look at it and scratch your head and say whether there is a Hamiltonian cycle or not. I tell you there is a Hamiltonian cycle. I am not going to show you what the Hamiltonian cycle is. Okay. And then I say, can you find some cycle in this graph which visits all the points? Now you are allowed to repeat vertices. Find the smallest cycle in this graph which visits all vertices. Do you understand my question? I am promising that there is a Hamiltonian cycle, but I will not show you the Hamiltonian cycle. I will say, okay, with this promise, work with this promise, and now can you find a small cycle in this graph which visits all the vertices, right. So, so here for instance, if you had given me this graph, I would have said the following, you are cheating, this graph is not Hamiltonian. Why is this graph not Hamiltonian? Look at these two vertices, vertices 2 and 4, right. Suppose I were to remove these two vertices, yeah, what happens if I remove these two vertices? So, I remove So, the graph breaks up into 3 pieces. There is one piece which is just this 3 vertex, one which is 5 and one which is this edge. If a graph is Hamiltonian, if a graph has a Hamiltonian cycle in it and I remove 2 vertices in the graph, suppose there was a cycle, there was actually such a cycle in the graph, and if I remove 2 vertices, how many pieces will I get? At most 2. Why? Because look at the edges of the cycle, these edges will remain, right? When I remove, there could be other edges also, right? There could be a whole lot of other edges. Maybe there are even other edges going like that. Even if there were no edges going like that, after I remove these 2, these other edges would remain and the graph would be at most in 2 pieces. That graph that I had was getting split into 3 pieces. What does that mean? That means that there was no Hamiltonian cycle in the graph. You were cheating. So, this is the kind of an argument I would like to use to be able to say that if your promise, if you had held on to your promise and that really the graph that you gave me was Hamiltonian, then I should be able to find a small cycle in the graph, right. So, let me formally write that statement down. So, we would want to prove something like theorem, if G is Hamiltonian, no, okay, this is trickier to write because let me not waste time writing the exact theorem, but assuming that you have held on to your promise that you have given me a Hamiltonian graph, I should be able to find a cycle in the graph which is of length 4/3 times the number of points. Remember, if there is a Hamiltonian cycle in the graph, right, like we had here, what is the length of the cycle? It's 5, and how many vertices are there? 5 vertices. So, the length of the cycle will always be equal to the number of vertices. So, I do not know what that Hamiltonian cycle is because you have not told me that Hamiltonian cycle, but I would like to be able to find some cycle which is small and which is within. So, want to find, so let me not, so want to find a cycle which is of length at most 4/3 times n, right. So, this is actually a very challenging problem. Lots of people have been looking at it, working on this, and it's a simple graph simple to state graph theoretic problem, right. Nothing else that's needed. Assuming the graph is Hamiltonian, can you find a cycle which is of length within 4/3 n? You are allowed to repeat vertices now. So, there are lots of such problems which are very easily accessible to researchers, for undergraduate students even, but very challenging nevertheless, right. It's easy to understand but hard to solve.
So, is there any general approach to find an algorithm for any kind of problem?
Yeah, there are lots of approaches. So, in our algorithms course, we teach students, 4 or 5 different standard approaches to try and solve problems. So, these will usually be applicable when the problems that you are trying to solve have efficient algorithms, so are in the class P. And when the problems that you are trying to solve do not have such efficient algorithms, then a different set of approaches are usually used, right. We use a lot of linear programming, even convex programming to formulate many of these problems and design solutions of them. So, there are lots of approaches, but usually every problem has its own idiosyncrasies, right. It will have something special, so that a general approach would quite often not just, you cannot just apply a general approach and solve that problem. There will be some intricacies, some clever way of putting together many different things that will yield a solution to the problem. So, yeah, if your question was, how difficult is it to solve some of these problems, it's actually very challenging, because while we do have a fairly rich set of tools, nevertheless, these tools have to be used in very clever ways, and many of these might have to be used together to actually solve a particular problem. One very important problem in computer science, and also it finds a lot of application in cryptography, is the problem of checking if a certain number is a prime, right? So that's called primality. So is n a prime? Okay, of course, this n is not n. I give you a number, let's say 3267555, and is this a prime? Okay, oh, it ends with a 5, right? So it's not a prime. But let's say it ends with a 7, then is that a prime? So this was actually a problem that is very useful in cryptography, right? There are many cryptographic schemes which require prime numbers. And how does one find, and not just require a prime number, you can't just say a 2 or a 3 or a 5 and run that scheme. You require a prime number which is, let's say, a 100-digit prime number, right? And so one way to generate a 100-digit prime number is to take a random number of 100 digits and then ask, so suppose we had an algorithm for primality, right, which given a number n would say yes or no, whether this is a prime or not. Then you give this box the number, that random number you generated, and if it says yes, then you got your 100-digit prime number. If it says no, you will try again, right? This is how primes are generated, large primes are generated. And this is very important, right, because a lot of your cryptographic protocols are just relying on these prime numbers. So it's very important to have such a box, and you want an efficient algorithm for this, right? How would you check if a certain number is prime, by the way? Right? The way we do it in school is we say, okay, let's try dividing it by 2, and then we try to divide it by 3, and then 5, and then 7, and then 11, and so on and on. Basically, you try to divide it with all the smaller prime numbers. If it is not a prime, it will get divided by one of these numbers. But how many times will you have to do this check? Right? If you just go in this simple way, then if n is the number that you are checking for, then you will have to do roughly square root n divisions, right? So the naive way will require a roughly root n divisions, right? Now what is root n? How large is this number root n? If n was a 100-digit number, then how much do you think is root n, right? So how large is a 100-digit number? What is the value of a 100-digit number roughly? So a 100-digit number is roughly 10 to the 100, right? Or if you want to be more accurate, it's definitely larger than 10 to the 99. And then if I say square root n divisions, what does this mean, right? So this means that the number of divisions I will need in this case will be roughly square root of 10 to the 100, which is about 10 to the 50 divisions. You will need so many divisions to check if a 100-digit number is a prime number or not. Now 10 to the 50 is huge, right? I said 2 to the 40 is an estimate of the number of particles in the universe, right? You cannot have a running time of this and hope to solve such a problem, right? It will take years for the fastest computer to be able to do this. So you want a better algorithm, a faster, a more efficient algorithm for this. Efficient algorithms were known, but required what we call randomness. And so Manindra Agarwal, who was a professor at IIT Kanpur, and 2 of his undergraduate students, they came up with an algorithm for this problem, for the primality testing problem, which is efficient, which doesn't require so many computations, right? So it will require number of computations. If it's checking a 100-digit number, it will require maybe 100 to the 4 computations. 100 to the 4 is very small. It's only 10,000 units, right? And it can be done in a fraction of a second. So that was a very major result, to come out of India in computer science. And yeah, so as I said, primality is important for cryptography. A lot of cryptographic protocols require prime numbers. There are many such problems from all areas of computer science, which find tons of applications. There are many such problems which find tons of applications in many different areas of computer science. And this, however, this primality problem was not known to be, for that, as I said, there were efficient algorithms known, but they required randomization. And the Agrawal, Kyle Saxena result, the AKS result, gave a efficient algorithm which did not require any randomization at all. And so it was a big leap forward. As far as problems which are, for which no efficient algorithms are known, there is one problem which is likely to be a problem where no efficient algorithms are known now, but in the future it is possible that someone comes up with an efficient algorithm for it. And this is a problem called graph isomorphism. So without saying it formally, so think of it as, suppose I have a molecule, okay, and or a protein, let's say, right? Many of you are from a biology background, or you would have done some biology. Suppose you had a protein, right? And another way, let's say a different way of representing that protein. Or now the question is, are these the same molecules or are they different? Is there a way of mapping one to the other? Okay, if this example is not very clear, I can go back to the graph terminology and ask you, suppose this is one graph and suppose this is another graph. Are these graphs the same or are they different? Right? Actually, they are the same. All I have done is I have taken this arc and drawn it in this manner. So these are the same graphs. This is a very trivial example. So this is what's called the graph isomorphism problem. I give you two graphs and I ask you, are these the same graphs? Right? Is it just that I have maybe numbered the vertices and the edges differently, and they are inherently the same graph? And you can imagine that this has lots of application, right? This in checking if two structures are identical or they are different. Now this is one problem for which is not known to be what we call NP hard. It's also not known to have an efficient algorithm, but there have been recent results which raise hope, which make it likely that in the foreseeable future this might have an efficient algorithm.
So sir, I always kept wondering that what exactly would be the application of finding whether a number is prime or not. As you mentioned, in cryptography it somehow comes into picture. Could you give a small example, real life application where knowing a prime number is important, like a detailed explanation of the example?
So as I said, the applications are primarily in cryptography. And one particular cryptographic protocol is what's called RSA. So RSA is a cryptographic. So what is cryptography about? It's about I want to send a message to you, and she should not be able to understand or decipher my message, right? So I want to send a message to you in such a manner so that no one else in this room can understand what is the message I've sent to you. So yeah, so we could put it in this form. So you have Alice and Bob, right? Alice wants to send a message to Bob, and should be sent in such a manner so that no one else is able to figure out that message. Now there is a very nice scheme for what is called public key encryption. Okay, what is public key encryption? So one way of sending this message is that we decided in advance, me and you, that we are going to encode the message in this manner, right? Let's say I said A, if I see an A, I will map it to T, I'll replace it with a T. If I see a B, I'll replace it with an X If I see a C, I will replace it with a Z, and this mapping I and U decided in advance. And now you can imagine that if someone does not know this mapping, it is going to be hard for them to figure out what the message is. But that for that to happen, I and U should have met at some point and decided on this mapping in advance. Now, this is not always feasible, right? Imagine you are buying something from Amazon or some other website. Now, you and that website have never met, right? You could not have decided on some key in advance. What you want to now, and why do you need to send messages securely to that site? Maybe you want to send your credit card information, right? So, you want to send your credit card information in a secure manner to that site so that no one else can, who is maybe accessing your network connection, can see what is the credit card information you sent, what is the password you sent, etc., etc. So, what is used is what is called public key encryption. In this public key encryption, it is a very nice scheme. The way it works is that each person has two keys. You will have two keys. One is called a private key and the other is called a public key. The public key is pasted on the wall. Public key of everyone is pasted on this wall. If I have to send a message to you, I will take this message and apply an algorithm on this message using your public key, right. So, the encryption procedure is that I take the message and I take public key of Bob, Alice wants to send to Bob, and then this is the encrypted message. And the nice thing about this encrypted message is that only you can decipher it using your private key. So, the public key and the private key form a pair such that something that has been encrypted with the public key of Bob can be deciphered, can be decrypted only with the private key of Bob, right. Remember I said everyone has two keys, a public and a private. The public key is public, the private key is kept private. So, in public key encryption for this scheme, right. So, it is a very beautiful scheme, and we actually teach it to our second year undergraduate students in a discrete math course. Maybe sometimes, I do not know, maybe even the first year computer science course, sometimes it is taught. It is a very beautiful scheme, and here it is very critical that you have some prime numbers to build these keys, right. So, these public keys and private keys are built, are figured out in advance, right, and given to everyone, all the users who are using this scheme, and these keys are derived by using some large prime numbers. So, at this point I think that is all I will be able to say how these prime numbers are used, but there are many such protocols in cryptography which require large prime numbers.
So, I've heard that it's the case that if you solve one NP problem, then you've in principle solved all of the NP problems that there are. So, isn't it a better strategy to actually focus on one NP hard problem rather than working on many different problems as we are doing right now?
Okay, good question. It is indeed true that these NP problems have are reducible to each other, as they are called. Reducible means that if one of them can be solved exactly, then all the others can be solved exactly. So, that is the nice thing about this class of problems, which is why people believe that they are hard to solve. If you solve any one of the problem, then you can solve a million other problems efficiently, and so people believe that it is unlikely to happen. Now, this however does not apply when we are talking of approximation algorithms. If I can get a good approximation for one problem, that does not mean I can get a good approximation for the other problem, right. If I got a 1 point or 1.3 approximation for traveling salesman problem, that does not mean that I will get you know, a better approximation for some other let us say some scheduling problem or something else, right. So, this does not apply anymore when we are talking of approximation algorithms, and so for different problems we have to come up with, you know, different approximation algorithms. So, in fact, that was the case till about 25, 30 years ago, before the advent of approximation algorithms, people would prove that a certain problem is hard to solve, right, by reducing some other known problem to it, and then say, oh, this is a hard problem, now I can't do anything with it, right, and they would just leave it. But then when people started looking at approximation algorithms, researchers started looking at approximation algorithms, they realized that different problems they are all maybe hard to solve, but they are very different as far as the approximation is concerned. For some problems I can get very close to the optimum solution, but for some problems I cannot get close to the optimum solution, and so they are actually quite different, these problems. So these approximation algorithms has helped us understand the differences between these various problems, which were earlier just clubbed into one class as, oh, these are all hard. Now we know that there are varying degrees of hardness as far as approximation is concerned amongst these problems.